Now we have seen what entropy is, that it's an outcome of quantum physics and it comes in different forms. But why is it so important? Why is it relevant? And what it comes down to is that it distinguishes between processes being able to work, all those that just produce entropy, and to those that produce work. So that means lifting, accelerating things, driving chemical reactions, and so on. Those processes are actually also limited by entropy in the second law, and this is what we're going to look at in more detail here today. So, when you have a disequilibrium, then there are two very different ways by which this disequilibrium can be depleted. So, if we have an energy source that maintains low entropy, then on the one hand side, we can deplete it just without work, just dissipate it, just, like, well, actually examples for this are radiative transfer or diffusion or mixing. It's like if you have a piece of wood, you just burn it and don't do anything useful with it, just burn it. The other option is that we actually generate work out of it, and this is shown here on the right. So, for instance, I like to use the example of a power plant as a process that performs work. So in a power plant, you burn something, create heat at low temperatures. That can generate power in the form of electricity, so it's useful energy. And this useful energy is then afterwards being dissipated when it is being consumed. So that's a different way of utilizing a low entropy energy source. This useful energy can then actually also be converted further into different forms of energy and other forms of disequilibrium, so it can perform further work and further work and further work. And examples in the Earth system for these kinds of processes that perform work is convection, atmospheric convection, it's dehumidification associated with a hydrological cycle, or charge separation, for example, in photosynthesis or photovoltaics. And to show how entropy limits the amount of work that can be done, I want to go a little bit more in detail of a power plant. So let's look at a power plant. This is here a coal-firing power plant south of Leipzig. It burns coal, creates heat by combustion, low thermal entropy. What comes out is what's called a waste heat flux here through the cooling towers. It's cooled by evaporation. So here there's heat being exported, but it's exported at a much lower temperature. And if you remember Clausius, delta Q over T. So when you export heat at a colder temperature, you actually export higher thermal entropy. And somehow in this process, there is some useful energy or free energy with no entropy being generated in form of electricity. Now, the two laws of thermodynamics apply to this. The first one is that energy is being conserved. So the heat that's being added by combustion, the heat that leaves the power plant through evaporation in the cooling towers, and the electricity generated, they need to balance each other. That's the conservation of energy. The other constraint is through entropy. And that is that whatever entropy is being added here, so we have an addition of low entropy heat because it's low entropy because the combustion generates high temperatures. We have the export of high entropy here with that heat flux. And overall, this power plant needs to satisfy the second law of thermodynamics, which means that there has to be at least as much entropy coming out of that cooling tower then, or even, there needs to be at least as much entropy being exported out of the cooling tower than what comes in through the combustion process. And we can write this in form of an entropy budget, and that's shown down here. So we have that the entropy export is equal to the entropy import, and maybe there are some processes inside the power plant that are not efficient and they produce entropy. And this is sort of where the second law enters here. This is the condition that this term here, this Greek symbol sigma, that needs to be larger than or equal to 0. In the ideal case, we don't have that. And then we have two equations, and we want to know how much power can we ideally at the limit generate. And from that, we actually get what's known as the Carnot limit of a heat engine or Carnot limit of a power plant. So it says that the rate by which work can be performed is proportional to how much heat is being released. And we see here this efficiency term. That's the Carnot efficiency that we saw in the introduction of the series. Now, how does it apply to the Earth system? Well, we can think of, or when we look at a landscape like here in Italy in the spring, sunny day, sun heats the surface, warms the surface. On the other hand, the atmosphere cools by emitting radiation to space. Then you have a temperature difference. You have a warm surface and a cold atmosphere. Temperature difference, just like a hot cup of coffee, represents disequilibrium. The other arrows that I put here are basically, that you also have emission of radiation to the atmosphere, and then the atmosphere radiates back, which is the greenhouse effect. But anyway, what it does, so this absorption of sunlight creates disequilibrium, and this disequilibrium, this temperature difference, can be used by a power plant, let's say an atmospheric heat engine, that generates work out of this disequilibrium. It generates motion. With motion, heat is being transported, but also moisture. So it convects. It's what one would call dry convection. So you bring material up, and eventually the kinetic energy of the generated motion is being depleted by friction somewhere and being converted back into heat. And now, how does entropy constrain this setup? Well, so the more power this power plant produces and the more motion it causes, and the more heat it transports from the surface to the atmosphere, the more it depletes the temperature at the surface. So, in other words, it depletes this temperature difference, it depletes this disequilibrium, and this is shown here in that schematic diagram. So the greater the heat flux, the less the surface temperature. Because of this, we can actually identify a state that represents maximum power. It's the maximum power output of that heat engine. And if you remember in the introduction, I was mentioning work by Lotka and by Eugene Odum about maximum power. Well, this is exactly one of those maximum power states. Well, recently, in the last few years, a PhD student of mine, Sarosh Gausi, he applied that in his thesis. So we used radiation data sets here shown on the left. So that's the heating of the power plant. So this is, or the heating of the surface actually. So it's the absorption of solar radiation here shown on the top, and the what's called the downwelling long-wave radiation. So that's the radiation that the atmosphere emits and that is being absorbed at the surface. Just a little aside, we notice that this one here is actually a lot bigger. It's about 2 to 3 times larger than the heating by the solar radiation, which also emphasizes the importance of the atmospheric greenhouse effect. Then we can apply the maximum power limit and generate maps from this input of heat fluxes and temperatures and compare these to observations that relate to the satellite product here from NASA. And we see here on the top, it's a comparison of the heat fluxes here estimated from this satellite data set and the ones inferred for maximum power, or down here, in comparison of the different grid cells in terms of temperatures being from the data set of satellite derived data set or derived from maximum power. And we see that the correspondence is very, very nice and very, very high. So what it suggests is, the atmosphere actually works at the maximum power limit, and it has to do with entropy and the Earth system. And we will soon see later how life fits into that. I already want to give a little taste. So, for example, when you look at a rainforest, one can take this approach further and actually look at how does energy get partitioned during the course of the day. So nighttime, then the sun rises, heats the surface, and the surface evaporates, and it creates updrafts and so on, and called the sensible latent heat flux. And this graph actually compares this for 2 months in the rainforest at a site Tanguro, close. That's a site, an observation site where our institute is involved in. And here on the left-hand side, in June 2016, June is the dry season in the southeastern Amazon, and here on the right-hand side is the wet season. The symbols show observations here averaged over the month, and the lines show what is estimated, or either is the input or what is estimated from this maximum power limit. And there too, you can see that it corresponds very well. So it seems like that rainforest actually, the energy partitioning over this rainforest is set by thermodynamics, essentially. One can also take it further. For example, very recent work deals with the diurnal temperature range. It means that, when you look at the course of the day and sun rises, then solar radiation increases, peaks around noon, and then descends. You have sunset. And associated with this strong heating by solar radiation is that the lower atmosphere actually heats up. It builds up a temperature difference between the morning hours and the late afternoon hours called the diurnal temperature range. So this is sort of illustrated here in the bottom diagram, and one can sort of also infer this diurnal temperature range very well compared to observations at a network that's called the FluxNet, and here compared to what's estimated for maximum power. One can then further translate this into what's called the water vapor pressure deficit. It's a measure for how dry the atmosphere gets during the day. And here too, we can see that the correspondence actually works really well. And for those who are interested, well, there is a slight effect of water stress. So in other words, when the surface does not evaporate because maybe you're in a desert or no access to soil water, then actually what happens is that the diurnal temperature range actually increases. And in this publication that is in press in geophysical research letters, we actually have an expression where we can quantify this magnitude. Again, basically it's a combination of thermodynamics and entropy with the specific settings of the land surface atmosphere system. Coming back to sort of the larger scale of the Earth system, well, we can then distinguish between processes that just dissipate this disequilibrium that is being created by the difference between solar radiation and the radiation emitted to space, and to those processes that actually perform work. This is what's summarized in this diagram. So again, we have the input of solar radiation here, low entropy radiation from the sun. Then it either gets thermalized, it gets converted into heat upon absorption. That means it's just being dissipated, no work being performed, or it radiates in the atmosphere, it's absorbed by the atmosphere and radiated back. That's called radiative transfer, also doesn't perform work. Now, the interesting processes are shown here on the right, because here we have the power plant. This is what we just saw in terms of this lovely Italian landscape where atmospheric motion in the vertical or also in the horizontal basically performs work from the disequilibrium that solar radiation generates. But we also have here photosynthesis as a process that performs work, and it performs work before solar radiation is being thermalized. So it means the photosynthesis utilizes the low entropy radiation of the sun. And another example is actually photovoltaics, which also performs work from sunlight. It performs the work of charge separation, and then afterwards this free energy in form of electricity can perform work. When we talk about the biosphere, well, photosynthesis also performs charge separation, then converts it into chemical compounds with free energy, which is basically carbohydrates that then fuel the biosphere. Now we can also ask, well, what's the effect of doing this work? And I want to come back to this example we had early on about this hot cup of coffee. If I use a spoon and stir that cup of hot coffee, then it cools faster. So in other words, when there is additional work being performed, what it results in is that the whole second law is essentially being accelerated. When we take this back to the whole system, then we can think of the Earth system almost like a layered system. Actually, this diagram I call the onion. So where you have heat generates motion generates maintains cycling of water and carbon and other substances. Then there is life that depends on cycling. We will see that very soon. And humans need life to feed. Then there's these processes that perform work, but then we have important interactions. Motion depletes heating differences. Cycling depletes heating differences. Life alters radiative properties. And so there are interactions taking place in the Earth system that we need to consider, all done by work being done. This work enables the dynamics that actually result in these interactions and overall in a faster depletion of the disequilibrium that is being caused by the absorption of solar radiation. So to sum these parts up, well, we saw that entropy is really relevant because it tells us about the usability of energy. It relates to this term free energy, the ability to perform work or generate power, power being work done by time. We saw how it limits the work, this example of the power plant and the Carnot limit to the work output of this power plant. And then we saw that climate essentially operates at this limit, and that includes the interaction between the work done in the atmosphere and what the results are or the effects are at the surface in terms of cooler temperatures. It accelerates the depletion, and also we will see that actually these heat engines set other constraints that are really relevant to the biosphere, and this is where we will go on next. In the next video, we will talk about what is life.